Now we're ready to discuss what to do with the results of calculations involving measurements. Recall that every time we make a measurement, there's always some uncertainty attached to that measurement, so it should make sense that any calculation we do with those measurements also has some sort of certainty attached to it, some sort of error attached to it. So we want to make sure we properly learn how to round the result of that calculation to properly imply the correct amount of uncertainty. In today's video, we'll talk about addition and subtraction rules. In the next video, we'll talk about multiplication and division rules. And it's important to learn what the rules are, but just as important to learn why those rules are what they are, the rationale behind those rules. So the addition and subtraction, our approach is we're going to round the result of our addition and or subtraction calculation so that its last significant figure is at the same place, the tenths place, the hundredths place, the thousandths place, etc., as the last significant figure of the measurement of highest uncertainty. The measurement that we have the least confidence in is going to dictate how much confidence we have in our final answer. So do a couple examples. We have 20.0 grams plus 0.505 grams. Our calculator gives us the answer is 20.505 grams. Our first measurement has three significant figures. The last significant figure here is in the tenths place. For our second measurement, we have three significant figures as well. But our last significant figure here is in the thousandths place. The tenths place is a larger uncertainty than the thousandths place would be. So then our answer is going to be limited to the tenths place as well. So we have three significant figures. The first non-significant digit here, the 0, is less than 5, so we round down. It gives our final properly rounded answer of 20.5 grams. Our second example is similar. We have 20.0 grams again, plus 0.500005 grams. As before, we have three significant figures here. Our uncertainty is in the tenths place. Our second measurement has six significant figures. The uncertainty here is in the millionths place. Tenths place versus the millionths place. Once again, this measurement has more uncertainty attached to it. So it's also going to limit how many significant figures we have in our final answer. So we're limited to the tenths place here. So once again, we have three significant figures. So the same answer, 20.5 grams. Our third example is a difference, 42 milliliters minus 0.03 milliliters. Two significant figures. Our uncertainty here is in the ones place. Just a one significant figure. Our uncertainty here is in the hundredths place. Ones place is larger uncertainty than the hundredths place. So our answer is also limited to the ones place. Our first non-significant digit here is 5 or greater, so it rounds up. So 41.7 milliliters becomes 42 milliliters. One more example, this one involving scientific notation. With scientific notation, we have to be a little bit careful because before we can apply our rule, we want to make sure that the exponents of two or more measurements are all the same. Here we have 3.10 times 10 to the third milliliters plus 2.0 times 10 to the second milliliters. So if we're not careful, we might have this logic. We might say, well, we have hundredths place here, tenths place here, so our final answer then would be good to the tenths place, and 3.3 times 10 to the third would be our answer. But that's actually incorrect because the exponents are different. Before we apply our rule, we need to make sure that these exponents are, in fact, the same. So to do that, I'll rewrite the first number. I'll convert this number so it has the same exponent as the first measurement. So this becomes 0.20 times 10 to the third milliliters. Now that the exponents are equivalent, now I can apply the same logic. We're good to the hundredths place. We're also good to the hundredths place, which means my final answer is also good or significant to the hundredths place as well. So the answer would not be 3.3 times 10 to the third milliliters, but rather 3.30 times 10 to the third milliliters. Now let's understand the reasoning behind these rules for addition and subtraction. This is example A from earlier, 20.0 grams plus 0.505 grams. We have three significant figures. This digit, the 0, in the tenths place is our last significant figure. It's our first uncertain digit. And so if this is our guessed at digit, in other words, it means we have no idea what's in the hundredths place. Likewise, we have no idea what's in the thousandths place and no idea what's in even the 10,000ths place. Likewise, 0.505 grams means I'm confident it's 0.50 something. I'm guessing here in the thousandths place, which means I have no idea what's in the 10,000ths place. So if we were to add these two measurements together by hand, we'd get question mark plus question mark gives us a question mark. Question mark plus 5 gives us a question mark. Question mark plus 0 gives us a question mark. 0 plus 5 gives us 5. Decimal point drops down, 0 and 0, 0, and then finally 2 drops down as well. So our final answer in grams is 20.5 question mark plus question mark plus question mark. In other words, 20.5 grams. Notice that our final result is limited to agree the same place, its last digit figure is the same place as our measurement of highest uncertainty, the 20.0. That's one way to think about this result. One more way to think about the rationale behind these rules is if I have a measurement of 20.0 grams, that means I'm confident it's 20 point something, and I'm guessing here in the tenths place. Another user might say it's 20.1 grams or 19.9 grams, typically plus minus 1, that last digit. So another user might say, well, they didn't find it's 20.0 grams, they may have found it's 20.1 grams. 20.1 grams and 20.0 grams have the same meaning because only where they disagree at is in the guess that digit. Likewise, 0.505 grams, it would be equivalent to 0.506 grams because we are allowed to differ in that last guessed at digit, the last figure of our measurement. So if a different user or a different instrument got these masses rather than these masses, our calculated result will be different mathematically, but as we'll see, it will have the same meaning scientifically. Because 20.606 grams, 20.606 grams versus 20.505 grams, where it first differs here is in the tenths place, which reinforces the idea then that our final result is good to tenths place because this first measurement is also good only to the tenths place. So rather we think of it this way where we can change the last digit figure in the measurements and see what happens to the result. That allows us to determine the rule for the calculations, or do it by hand. Either way, we can come up with a rationale for this rule. Next time, we'll talk about what to do with the results of multiplication and division problems, how to make sure that those results are properly rounded to the correct number of seven figures. I'll see you then.